All right, let's go over how to solve for the internal and external forces of a truss using the method of joints. Okay, so if you're going to follow along on your own paper, the first step would be to redraw this truss on your paper and then also establish a coordinate system. I like to use the same coordinate system every time. The one I use looks something like this. Going to the right represents a positive x, going up represents positive y, and going counterclockwise represents a positive moment. Okay, so once we've redrawn our truss and established a coordinate system, our next step is to see if our truss is statically determinate. And if you remember, the equation is 2j is equal to m plus r, okay, where j is your joints, so j is for joints, m stands for number of members, and r stands for number of reaction forces. Okay, so now we've got that. Looking at our guy here, we've got a joint at A, we've got a joint at B, a joint at C, and a joint up here at D. Okay, so that's going to give us 4 total joints. So 2 times 4 is equal to M, number of members. We've got joint AB, joint BC, joint BD, joint AD, and joint CD. So that's 5, or members, sorry, those are all members. So it looks like we've got 5 total members. And reaction forces, remember our pin joint here gives 2 reactions, and a roller joint gives 1 reaction. So it looks like we're left with 3 total reactions. So 2 times 4 is 8, and 5 plus 3 is 8. So 8 does in fact equal 8. So this guy is going to be statically determinate. Okay, so the next thing that we need to do is solve for any missing side lengths or angles that we might have. Okay, so we're looking at this guy up here. I'm going to break that into 2 right triangles, and I'll draw the first one down here. It's going to look something like this. Just like that. We know that the side length here, okay, hold on. Side length here was 5, side length here was 4, and we need to solve for the angles. So what I'm going to do is I'm going to solve for this angle here. This is the angle at joint A, so we're going to call this theta A. What I have is the opposite side and the adjacent side to this. Having both of those, I'm going to use our function tangent. Remember, tangent of a theta is equal to its opposite side length over its adjacent side length. So in our case, if we are solving for the tangent of theta A, it's going to be equal to 5 divided by 4. But to get theta by itself, we have to take the tan inverse of each side, which is going to give us theta A equal to the tan inverse of 5 divided by 4, which is going to be equal to 51.34 degrees. Okay. So now that we have that, we can go back up here. This guy here is 51.34. And then since these are mirror images of each other, this side over here is also going to be 51.34. And then if you do a little bit of math, remember that these were right triangles, your interior angles on a triangle add up to 180 degrees, which means that both of these angles up here are going to be equal to 38.66 degrees. Okay, so now we've redrawn our truss system, we've established a coordinate system, we've determined that this is in fact statically determinate, and we've solved for any missing angles and side lengths that we've needed. Okay, so that's kind of the first step in setting up your problems. Obviously I had some other steps kind of in between. So now we're going to look at a free body diagram. So remember we had a pin joint. Actually, let's do this. Grab this whole thing. Scooch over a little bit. Okay, so we had a pin joint at A here, so this was A. So now we're going to solve for the external forces. So we had a pin joint here, so that's going to have a vertical force and a horizontal force acting on it. And then we're going to have a roller joint here at C. So that's just going to have a vertical force. So I'm going to guess that since F2 is going to the right, that our reaction force A in the X direction is going to be going to the left. And since F1 is going down, I'm going to assume that our reaction force at A in the Y direction is going to be going up. And the same thing for our reaction force at C in the Y direction. I'm also going to assume that that guy's going up. Alright, so you can already see that I've got this first equilibrium equation written down. That is the sum of the moments about any point is going to be equal to 0. Remember that most of the time we're going to want to pick a joint or a pin joint. It's going to make our life as easy as possible. So if we're going through and solving this guy, if we add up all the moments, you would have the moment at A caused by the X component. You would have the moment at A caused by the Y component. You would have the moment caused by F1 about A, which looks like that's going to put us in a clockwise direction. So that one's going to be negative. Okay, so moment caused by F1 is going to be negative. Same thing for our moment caused by F2. Looks like it's going to push us in the clockwise direction. But our moment caused by our reaction force at C in the Y direction looks like it's going to push us counterclockwise, so that guy's going to be positive. So positive moment CY, okay? So remember that both of these guys are going to go to 0 because the distance at point A is 0. So that one's pretty self-explanatory. MF1, remember that was 4, so it's 4 times 500. MF2 would have been 5 feet, so 5 times 300, and then plus 8 times RCY. Okay, and we're solving for RCY here. Move that stuff around, you get 8 RCY is equal to 3,500 foot-pounds. And then you get RCY is equal to 437.5. Okay, so we've solved for our first external reaction force. Okay, so let's sum the moments in the Y direction, all of our external moments in the Y direction. Those also have to be equal to 0. So the way we drew it we had RAY going in the positive direction, RCY going in the positive direction, and F1 going in the negative direction. So this should be RAY plus RCY minus F1 is equal to 0. Okay, so we don't know what RAY is, so we just rewrite that. RAY. We do know what RCY is now. It's 437.5. And F1 just so happens to be 500. All that is equal to 0. So you do a little bit of math. You figure out that RAY is equal to 62.5. Okay? So now we've got our second external reaction force. And then we go on to solve the forces in the x direction, which also have to be equal to 0. In this case, we had 2. If we go back up here, we've got RAX and F2. RAX is going in the negative direction. F2 is going in the positive direction. So go back down here. We've got minus RAX plus F2, which is 300, is equal to 0, which just means that RAX is equal to 300. Okay, so that is our third and final external reaction force. So we're doing pretty good. Okay, so the next thing that we need to do is a little bit different. We need to draw a new free body diagram. Okay, so this one is a little bit different. Basically, you're going to want to outline or highlight the location of the truss members instead of just drawing them with a line like we have previously. Okay, so this is going to help you out a lot because now we're going to add in what we think the internal forces are doing. Okay, so we're going to first draw our external forces. So we had F1 here, like that. We had F2 here. We had RCY, RAY, and RAX. Just like that. So now we've got all of our external forces. So what we're going to want to do now is try and figure out what we think is going on inside of the members. Okay. So basically we're going to just take a guess at what we think is happening, internally. Okay, so RAX, let's look at joint A here first. So we're looking at joint A here. RAX is going to the left. So in member AB, so this is AB, I think that there is going to be an internal force going this way, opposing that force going that way. So we can call that the force in AB. Okay. And then we have RAY going up. So I think that something has to oppose that. So this is member AD. So I think that AD is going to be going down this way. So the force of AD is acting in that direction. Okay. So if we take a look at member B here, we've got F1. So this is BD here. F1 is going straight down. So I think B is going to be reacting in this way. So we'll call that force inside of BD. Okay. Then I think you've got force AB going to the right. So force B here. Okay, so if you are, let's talk about this first really quick. If I've got a member and I've externally put this guy in tension. Okay, so tension is me pulling it apart. Okay, so that's what it looks like on the outside. But on the inside, it's gonna try and hold itself together. Okay, so if I am pulling it apart, internally it's gonna be going together. Okay, same thing if I did that the opposite way. So if I have a member in compression, which means that I'm pushing it together, internally it's going to respond by trying to push itself apart. Okay, so this first one is tension, and the second one is compression. Okay, so if I've already got that we're indicating on member AB that we're in compression, I can assume that this guy is also going to be going this way. Okay, I shouldn't have forces going in the same direction inside of my members. Okay, they should be going opposite directions, which means now I'm looking at B here, and I've got one going up, one going down, one going to the left, so I should probably have one going to the right, and that would be force of BC. So this was force AB here. Okay, not too bad. Then we can take a look at C. We've got RCY going up here. We already know that we have to have force BC going this way. We've got one going up, one going to the right. So why not have one going to the left, one going down and to the right, and call that force of CD. Okay. And then we move up to our D joint, flip that force back up there. This member looks like it's in compression, so that means we can add an arrow going towards D there. That's also the force of CD. Member BD looks like it's in tension, so we can add an arrow going this way, force BD. And then member AD looks like we've already drawn that in compression, so we can add an arrow here for the force of AD. Okay, so I know that can be kind of confusing, but basically we're just got to kind of figure out what we think is in compression and what we think is in tension. Alternatively, you could just draw everything in tension or everything in compression, and then just if you get negative answers, know that you drew those wrong, and then you can fix them. Okay, so now what we're going to do is we are going to take every joint here and analyze it as its own free body diagram. Okay, and that is going to allow us to systematically tackle this guy without kind of having to look at the whole thing at once. So we should be able to just knock it out and get all of our unknown members, so our internal forces, solved for. So if we look at joint C here, so joint C looks like that. It's got RCY acting on it. It's got this force, which we called the force BC, and then it's also got this force going down like that, which is the force CD. Okay, we could redraw this guy to look like this. Basically, I'm going to break it down into its components so that we can look at it better. Okay, that way we can sum our forces in each direction properly. Okay, so we've got joint C here again. Reaction force CY is already going in the Y direction. The force BC is already going in that direction. So we just need to break CD down. So we've got it going down and we've got it going to the right. So this is force CD in the X direction, and this is force CD in the Y direction. Okay, so now all we have to do is pretty simple. We just got to sum our forces in the Y direction and then sum our forces in the X direction and solve for any unknowns that we can get. Okay, so the first thing we're going to do is solve our forces in the Y direction. Remember, those have to be equal to 0, and those are equal to RCY positive minus the force CD in the Y direction. Okay, RCY was equal to 437.5, and we don't know force CD in the Y direction. Remember, those have to be equal to 0. So that just means that force CD in the Y direction is going to be equal to 437.5. Okay, so we know that. So now we need to sum our forces in the X direction equal to 0. We had force CD in the X direction, and we have our force BC. Okay. And we don't know what either of those are yet. So I'm going to set those equal to 0. So to solve for force CD, so that way we can get CDX. So we and BC. First, we'll have to take a look at our triangle at joint C here. Remember, this was 4, and this was 5. Just kidding, we don't want the lengths here, we want the forces. So if we take that same triangle, right, and we call that force CD in the Y direction, and then force CD in the X direction, and then we have just force CD, and we call this guy right here our theta. We know that tangent of theta is equal to our opposite over adjacent. So that is going to be equal to, let's draw that down here. Opposite over adjacent, our opposite is CDY. So it's going to be 437.5 over our adjacent, which is what we're looking for, because our adjacent is going to be force CD in the X direction, is going to be equal to the tangent of 51.34. Okay. So with a little bit of movie magic, we know that our force CDX is going to be equal to 350, which means our force BC, so FBC over here, is also going to be equal to 350. And then if we use a cosine from our guy up here, we can do cosine of theta is equal to adjacent over hypotenuse, which is equal to 350 over FCD. Work that out, you get FCD is equal to 560.27. Okay, so we've got force CD here, and then we've also got force BC here. Okay, so it's a little messy. I hope you could follow along. That was joint C, and we solved 2 of our 5 members. Okay, so now we've got to go through and just keep going on with our joints here. So joint B looks like this. This is joint B. It had F1 right here, which was equal to 500 pounds. It had FBC, which we just solved for, which is 350 pounds. It had force BD, which we don't know yet, and it's got force AB, which we don't know yet. Okay, so if we sum the forces and the x direction, we set that equal to 0. We can have force BC goes in the positive direction, and force AB goes in the negative direction. So we can set those guys equal to each other, which just means that force AB is going to be equal to 350. That one's pretty easy. So that one's 350. And then if we sum our forces in the y direction, also set that equal to 0 because we're in equilibrium. We had force BD going in the positive direction, and we've got force 1 going in the negative direction. Set those guys equal to each other, and we get force BD equal to 500. Okay, so joint B was pretty easy. All right, so that is 2 more of our members. So it looks like we've got just the 1 more member force to solve for here. Okay. So joint A, I don't know if you remember, joint A looks like that. It had RAY going in the positive y direction. It has force AB going in the positive x direction. It had RAX going in the negative x direction. And then it's got force AD here going in the downward and leftward direction. Okay, so we already know RAX. We already know FAB. So what we can do here to solve for AD is we can just solve in the y direction. So if we solve for the forces in the y direction, we set them equal to 0. we've got R, A, Y, and we've got the force going negative, force A, D in the Y direction. Okay, so remember you got to break that guy into components. So if we break that, sorry. So we break this guy into components, it looks a little something like A here. We would have RAX going this way, RAY going this way, FAB going this way, and then we would also have FAD in the Y direction, and then it would also go here, FAD in the X direction. Okay? Alright, so we set all that stuff equal to 0. We know that RAY is going to be equal to FADY, which is equal to 62.5. So now we've got what it is in the Y direction. We just need to know what force F or force AD is doing. Okay. So if we draw AD looks like this. So this force AD has its Y component, force AD in the Y direction, and then it's got this X component here, force AD in the X direction. Okay, so using that triangle, you remember we had an angle here. This angle is equal to 51.34 degrees. Okay, so if we have FADY, that's the opposite of our angle here. So we're going to use sine. Okay, so sine of theta is equal to opposite over hypotenuse. Okay, and we're looking for FAD, which is our hypotenuse. So this is going to work out great. So if we take the sine of 51.34 is equal to 62.5 over our hypotenuse. Okay, you multiply both sides by your hypotenuse and divide both sides by your sine. You get that your hypotenuse is going to be equal to 62.5 divided by the sine of 51.34 degrees, right? And then you get your hypotenuse, which is equal to FAD is equal to 80.04. Okay, so we have just solved all of our internal forces. So the very last thing that you want to do when you've gotten all your forces, and sometimes I actually like to do this kind of while I'm solving for all these things, is make a summary. Okay, so normally I do this kind of while I'm doing it. I'll go through and I'll write down a summary of everything that we've done so far, and I'll draw an updated free body diagram. Okay, so let's start with our updated free body diagram here. So we've got RAY here, RAX, and then we had force AB, and remember AB is in tension, which means it's got a force coming back this way also, force AB. We had F1 going down. We had force BC here. This guy is also in tension. Force BC coming back. We had RC in the y direction here. And then we had force CD. This member is in compression. We had force CD up here also. We also had F2 going this way. Looks like we had force BD. So this member is in tension. So we got a force there, force BD, D. And we also had force AD going the other way. Force AD goes this way, which means this member is also in compression, which means this guy goes this way. Okay, so that's all of our stuff. Looks like force or member AD and CD are in compression, and the rest of our members are in tension. So if you're looking at it and you put those certain forces on there, we know which members are in tension and which are in compression, which is very helpful to us as engineers. We also know the force that each of these members is experiencing. So if we're trying to choose materials or redesign a bridge, we can choose something that would be good enough. So force F1, just as a summary, was equal to 500 pounds, and its direction was in the negative y direction. F2 was 300 pounds, and it was in the positive x direction. RAY we solved to be 62.5 pounds, and it was in the positive y direction. RAX was 300 pounds, and it was in the negative x direction. RCY 437 pounds, or 0.5 pounds, sorry, and it was in the positive y direction. Now, like I said, when you're doing these problems, I like to set the summary up right after I make determine if something's statically determinate. In this way, you write down everything that you know and everything that you don't know, and then you know when you're done calculating, and you don't have to go back through and look at anything. Okay, so force AB. So the force inside of the member AB was 350 pounds. AD was 80.04 pounds. Force BC, 350 pounds. Force BD, 500 pounds. So I hope we picked a material for BD that can withstand that 500 pounds. And then force for CD was 560.27. So I really hope we picked a good material for that one. So this was just kind of a quick but also long overview of how we would solve for all of the external and internal forces in a truss system using the method of joints. So hopefully that was helpful for you guys.